Welcome back, everybody. This is part 2 of 5 in my series on radicals. In this video, we're going to look at some properties of radicals that are going to let us tackle more challenging problems. Let's get started. The first property of radicals that I want to look at is this multiplication property. We mentioned in the previous video that we cannot split radicals up over addition, or subtraction for that matter, which is true. But the good news is we can do that over multiplication, and that's really helpful for problems like these ones. For example, let's simplify each of the following. In part A, I can split this 225 up into its factors that might be perfect squares. How would I do that? Well, a helpful tool in doing so is called a factor tree. Let's look at the number 225 and list some factors of it. Two factors are 25 and 9. So I can write this as the square root of 25 times 9, and I know now that I can break this up over multiplication. So I can write this as root 25 times root 9, or 5 times 3, which is 15. So 15 is the square root of 225. Going the opposite direction, though, or using this property in the opposite direction, sometimes I might have a big, scary product of two radicals, but it makes sense to multiply them together so I can combine my like terms, like in this one. Here, I can write this all as one big radical. And remember, to multiply two expressions together, I multiply all their like terms together. 3 times 6 is 18. X to the 1 times x to the 3 is x to the 1 plus 3, or 4. Y to the 1 times y to the minus 2 is y to the 1 minus 2, or negative 1. And now this guy is a little bit more simple. We can simplify more from here, but we'll put a pin in that for now. Let's look at the next property. Just like I can split radicals up over multiplication, I can also split them up over division, so long as the denominator's not 0. Remember, I can't divide by 0. So let's simplify each of these guys. For part A, here, I've got sort of a complicated radicand, that's the fancy name for the thing inside the radical, 100 over 9. But I can split that up over the fraction bar. And now, both the numerator and denominator are perfect squares that I know. The square root of 100 is 10, and the square root of 9 is 3. So 10 over 3 would be the final answer. Why don't you pause the video here to see if you can do part B on your own direction, where I've got a really complicated radical over another really complicated radical. But if I combine them into one whole big radical, like I've done in my first step of my solution, then a lot of cancellation happens. 48 over 6 is just 8, and x to the 5th over x to the 3 is x to the 5 minus 3, or x squared. So all I'm left over with on the inside of the radical is 8x squared. And I can actually simplify that even further. By writing that as 2 times 4x squared, I can now split over multiplication just like I did in the first problem. And now what I'm left with is root 2, which doesn't simplify, and root 4x squared, which is a perfect square. It's 2x. So I get 2x root 2 is my final answer. The last thing that I want to address here is that the distributive property works with radicals too. I can combine radicals almost like they're variables over addition, but really this is just the distributive property in reverse. So for example, down here, remember when I don't have a coefficient that's sort of like an imaginary 1 out front, which I definitely intentionally just drew funky so that you know it's imaginary. So if I've got $1 dollar and I lose $7, I end up with -$6. But they're not really dollars in this case, they're square roots of 5x. From this video, you should be taking away how to split square roots over multiplication and division to simplify them into bite-sized pieces. In the next video, we're going to take a look at a process called rationalization, which can help us remove radicals from some more hard-to-reach places. Catch y'all on the next one.